All right, so let's work on this one. So we just started talking about influence lines. We'll start off pretty slow. So I want to construct the influence line for the reaction at B. So what I'm going to suggest that you do is draw a free body diagram and identify the pieces that you're interested in. So here is the reaction at A, and here is the reaction at B. I'll assume they're both acting up. And just to give us some, these are 5 feet and 5 feet. And now I've got this unit load, my dimensionless load that's representing my moving load. I'm going to say from the left side it's at some distance x. So I'm going to solve for By as a function of the load moving from left to right. How do I do that? How do I normally find a reaction at say A or B? I usually sum moments at the other side. So let's do the same thing. So I will sum moments at A and put the whole thing in equilibrium. So what do I have about A? My influence load is creating what kind of moment about A with right-hand rule? Positive or negative? Negative. So the value is 1 and the distance is x. And then By reacts. What kind of moment is that? Positive. And that's By times 5 feet. So let's solve for By. What's By equal to? It looks like it's x divided by 5. That's pretty easy to plot, don't you think? So I'll come over here. Remember, I'm looking for By as a function of my moving load. And just to keep things in place, I'll extend a couple of lines here. So we just need to plot that. So at x equals 0, it is 0. At x equals 5, it is 1. And at x equals 10, it is 2. So that would be a value of 1, and that would be a value of 2. So where should I stand as a point load to create the biggest reaction at B? According to the influence line, I should stand right here. And again, let's say I weigh 200 pounds. What would be the reaction at B? Well, it's 2 on the influence line, so 2 times 200, 400 pounds. No matter where I stood in here, you would take my weight or your weight or whatever the weight was and multiply it by the ordinate of the graph. Yeah?
So did we just assume that it wouldn't change if it was on the right side of the...
Well, how would my equation here change if it moved over here?
Oh, it wouldn't.
So you've answered your question.
Yeah.
Good job.
Okay.
Well, since we got B, should we go ahead and get A? Even though the question isn't asked for. Let's do that. How can I solve for AY now? How do you normally solve for AY? Or any reaction once you have one? You could sum forces, right? Equilibrium is still there. It hasn't gone away. So what does my equilibrium equation say? It says that AY acting up plus BY acting up and then minus 1. So what is AY equal to? It is equal to 1 minus BY, which is equal to 1 minus x over 5. Can you plot that? I know you can. I know you can. I'm very confident that you can do this. So AY I'll go ahead and extend these lines just so you can see them. So let's start with this. So when x is 0, what is our value for x? I mean y, ay. Looks like it's 1. When x is equal to 5, what's the value? 0. What's the value when x is equal to 10? Minus 1. So your line can be both positive and negative. So when we draw this for shear force and bending moment, there'll be areas where the load is moving that will create a positive result and areas where it might create a negative result. Now, as a designer of a steel structure, do you care whether it's positive or negative moment? So you probably want the largest magnitude of the moment, not necessarily the sign. You know, a negative 50 is not smaller than a positive 50. Right? They're the same. They're 50. It's just direction. Remember, for us, sign is direction, not on a number line. What if you add these two together? What do you get at every point? 1. Shouldn't we?
Yes.
According to this, AY plus BY minus 1 should be 0. So if I add them together, I should get 1. Isn't that amazing? And that was the shortest problem we've ever worked. That was, with all the talking, that was 5 minutes and 32 seconds. So any questions about the shortest problem we've ever worked? Besides that? All right.